All right, guys, welcome back. So here's our last topic, Unit 4, talking about the applications of exponential and log functions, which is pretty much going into the idea of log word problems. That's what we got going on here, and exponential word problems. So our main type is based on the idea of continuously compounding interest, which you've seen interest at different points in your academic careers, pretty much involving money. The formula is based on A equals P e to the RT. A is the amount of the account after T years, P is the starting amount, R is the annual interest rate written as a decimal, and obviously T is in time. It has to be in years. So we got Joe investing $8,871 in a retirement account, fixed annual interest rate, 5.01% compound continuously. What will be the account balance after 20 years? We want to find the final amount. We want to find A. So A is 8,871 e to the 0.0501 times 20. And make sure that's all in the exponent position using your E button on your calculator. So we'll get our final value here to be $24,160.15. It's money, so we would not round to the thousands place. We only round to the hundreds place involving with money. So that's a straightforward example. Just plug in. It's all set up on the right side for the unknowns to fill into the formula, and you just type it into the calculator. Here we have Amy investing a sum of money to retirement accounts. We have this interest rates. Always make sure you're careful. They're giving you decimals for the interest rate, but it's a percentage still, so you have to still convert it. They give us the final balance after 17 years. They want to know the initial balance. So the 15,577.30 would equal P e to the 0.033 times 17. And while it may not look like it, that e to the power is just simply some sort of number, so we're just going to divide it over. Better off to divide over before you start trying to type into your calculator. That way you're less likely to make a mistake with rounding errors or anything like that. And we should be coming up with a value of $8,889. No cents. It all rounds away to be a perfect whole number value. So those are your two straightforward examples. Trying to solve for the initial or final values is just, R and T. So that part is just a number, just either multiplying with P or dividing over with the A. When you're trying to solve for R or T, the variable in the exponent position, that's now where the exponential equation comes into play. And that's what we got here. Rob invests $2,839 into the retirement accounts, fixing an interest rate of 3.74% compound continuously. How long will it take for the account balance to reach $4,616.57? So we go ahead and start off with filling into our question here, filling into the formula. And again, we don't know T. So whether I'm solving for R or T, if I want to solve for the variable in the exponent position, we're dividing over the value of P here, where we are going to leave this in its fraction form. We're not going to attempt to write this as a decimal. It's probably not going to go out too well. And then we take the natural log of both sides, because we have natural log of that fraction. And then the E disappears because the natural log and E are inverses of each other. So we just divide over the 0.0374 from both sides to solve for T. Making sure, as I have written here, you've got the parentheses surrounding the entire natural log fraction, so it's properly dividing away. And this, based off rounding, comes out to just be exactly 13 years. Since it's not money, if it wasn't exact, we'll go to the thousands place. Anything involving money will go to the hundreds place. But T, if we're trying to solve for that, we'll go to the thousands. The interest rate, we'll put it back into percent form and then round it to the thousands place appropriately from there. So that's solving for time. Solving for R is the same exact process. We're setting our final value. Oops, sorry. Jumped the gun there. So our final value equal to our initial value, e to the 19R. Again, we're going to divide over the 2,861. And then we're going to take the natural log of both sides. We have the natural log of that fraction, 15,141.98 over the 2,861 equals 19R. We divide over the 19. So here you're going to be careful because you're going to get R as a decimal, but we want it as a percent form. So you're then going to multiply the result you get by 100. So it's going to give us 5.66% equal to our value of R. All right, so R's always need to be in percent for the final form, decimal into the equation because that's the only way it's going to work, but it has the final answer be in its percent form. All right, so that's our compound interest problems. In general, growth and decay is based off the same formula, just using different variables here. Y equals C e to the kt. The y and the c correspond to the a and the p, and the k corresponds to the r. C is our initial value. K is the constant proportionality determining growth or decay rates. K being positive if it's growing, K being negative if it's decaying. And then y is obviously the final amounts based off t, time. All this has to match up unit-wise, so just be careful with those things. If we're talking about years and they suddenly talk about months for the question, you got to convert that into years or vice versa. So we're going to talk about two main types. So there's obviously many different types. We'll talk about population growth for a growth question, and we'll talk about radioactive decay for a decay question. Now, when we talk about radioactive decay, we're typically talking about half-life questions. So we're going to need to solve for that growth constant, or in this case, decay constant first. And for a half-life question, it's actually kind of nice. K is always going to be ln of a half divided by whatever the half-life time is. Now, this is always going to give us a weird decimal. Sometimes it'll be in scientific notation format, sometimes just in normal decimal formats. You're going to need to make sure you store this exactly. So if you're not quite sure what I mean by storing your variable, you're going to stop this video. You're going to go over to the calculator usage video that's going to show you how to store variables, and watch that and get comfortable storing variables there, and then you can come back to here and store these different Ks. You want to make sure we're using the exact value throughout. So they tell us a radioactive isotope has a half-life of 200 years. They're currently 10 grams. How much will be there after 855 years? So we got to find K first. So we're doing ln of a half divided by the half-life time is 200 years. That's how long it takes to get to a half-life. So our K is going to come out to be approximately negative 0.00347. There's a bunch of other stuff going on there. Because of all those extra zeros, rounding to the thousandth place and using that might not be the best strategy. You're going to lose a lot. And also, in general, we don't like to round in the middle of the question. So you're going to go ahead and store this based on how you were shown how to store in the other storage video. I will call this K. I would store it as K just because it's a nice simple variable for this. You can store it as whatever variable you want, though. It doesn't ultimately matter. And so then our final value is going to be y equals 10e to this K value times 855. So your screen should look like that, 10e to the 855 alpha K for the storage spot, not typing in any sort of value you want for K. Just use the stored variable, and we'll get the exact value of 0.517 grams of this particular isotope. All right, your ability to store variables is going to come into critical detail in the next units. The trick unit involving law of sines, law of cosines. There'll be a lot of questions that you need to have multiple stored variables. For these questions, there's typically only one, maybe two, depending upon the question. Sometimes we'll have to store the initial value because we'll have to find it. And that's why, again, you want to get comfortable storing these different variables in each of these questions. All right, so here we've got a radioactive isotope with a half-life of 4 months. They're currently 45 grams of the isotope. How long will it be until there's only 5 grams left? So we want to find a time now. So I got to find K first. So K equals ln of a half divided by 4. This value is not as small as a decimal. This value is giving us a negative 0.173. Still storing it exactly. Still storing it as alpha K to use in the problem. Now we've got 5 equal to 45 e to the K times T. But we're trying to solve for t because we already know what k is. Either case, it's the exponent. We divide over the 45, which that fraction reduces nicely, so we'll reduce the fraction, though you don't need to. Take the natural log of both sides, so ln of 1/9. And then we divide over the exact value of k. So we divide over alpha k in your calculator, ln of 1/9, close the parentheses, divided by the alpha k. And you'll get our half-life time to be 12.68, and this would be months because they give us the half-life original time that we found K in was based off months. All right, so those are two simple examples of radioactive decay, how to find K and then use that to find a final value, use that to find a certain time. Those are the kind of style questions you'll see with the radioactive decay problems. Population growth, typically they're going to give you a population after a certain period of time. They're not going to give you the initial population. Though if they do, that's obviously a little bit easier. They give you C, but here we don't know C. So we're going to essentially create a system because we're going to have 125 equals C e to the 3K, and we're going to have 360 equals ce to the 5k. Notice we can't use k equals ln of 1/2 divided by the half-life time because it's not a radioactive decay question. So what we can do is the first question, we can solve for c by dividing over that e to the 3k. So if we fill that in, we'd have 125 e to the 5k divided by e to the 3k. Dividing subtracts exponents, so we get 125 e to the 2k. So we can divide over the 125. 360 over 125 equals e to the 2k. We could reduce the fraction, but again, it's not necessary. ln of both sides. And then divide over the 2 to get k by itself. So k is going to give us 3.526. Oh, sorry, I'm looking at the wrong thing. It's going to give us 0.529. Just make sure we store it as alpha k. And then we fill in to get c, so 125 over e to the 3 alpha k bun gives us 25.575. And you'll want to store that one also. So I've got that stored as c, and I got this one stored as k. Anytime you're using inexact answers that are rounded off, you want to make sure you're using the storing variable option. And they want to know what's happening after 9 hours, so you're just doing y equals c e to the 9k, using alpha c and alpha k to type in. And we should be getting approximately 2,986. We can't have a decimal of a bacteria, so it wouldn't make any sense to say 2,985.984, but 2,986 approximately bacteria. All right, so that's our exponential growth and decay word problems. Again, it's all really going to come down to your ability to store variables. As long as you can do that correctly and accurately, you should be perfectly fine with this concept. All right, that's it for units 4. So next time will be units 5. So as always, appreciate you watching, and I'll see you next time.